Hello, everyone. So for this session, we will be tackling big data analytics. Now that we have done the collection and transformation and loading of our data sets, so basically your ETLs or ELTs, we want to make that data available to our users for various analytical purposes. So before getting into that, some of the questions that you might want to ask is the kind of processing that we'll be needing for our data set. And in this context, you'll be hearing the terms OLTP and OLAP, or OLAP. And I have this excerpt from our main reference textbook, which is Designing Data-Intensive Applications. So I'll be reading this. Even though databases started being used for many different kinds of data, comments on blog posts, actions in the game, contacts in an address book, etc., the basic access pattern remains similar to processing business transactions. An application typically looks up a small number of records by some key using an index. Records are inserted or updated based on the user's input. Because these applications are interactive, the access patterns became known as online transaction processing or OLTP. However, databases also started being increasingly used for data analytics, which has very different access patterns. Usually, an analytic query needs to scan over a huge number of records, only reading a few columns per record, and calculates aggregate statistics, such as count, sum, or average, rather than returning the raw data to the user. For example, if your data is a table of sales transactions, then analytic queries might be what was the total revenue of each of our stores in January? Second is, how many more bananas than usual did we sell during our latest promotion? And lastly, which brand of baby food is most often purchased together with brand X diapers? These analysts or data scientists and feed into reports that help the management of a company make better decisions or business intelligence. In order to differentiate this pattern of using databases from transaction processing, it has been called online analytical processing or OLAP. To summarize those things, here are some differences of OLTP and OLAP. So for the main read pattern, in OLTP, only a small number of records per query, fetched by key. For OLAP, it's the aggregate over a large number of records. For the main write pattern in OLTP, it's random access and low latency writes from user input. In OLAP, it's bulk import, TLS or event stream. Now, next one is for OLTP, it's primarily used by the end user or customer via web application or some other platform. For OLAP, it's the internal analysts, the data scientists for decision-making purposes. In OLTP, what the data represents would be normally the latest state of data, in the current point in time. Whereas in OLAP, it's a history of events, historical data, basically. In OLTP, the dataset size normally is about gigabytes to terabytes, while in OLAP, it's higher, it's terabytes to petabytes. So from a data warehouse perspective, this is how it looks like. Now, again, you have your users feeding data to our system. Now, that would be your OLTP systems, the individual databases, tables that you have for various use cases. So in this case, you would see the e-commerce site, the stock keeping app, the vehicle route planner, and many other databases. That's OLTP systems. Now in OLAP, you will be utilizing those databases. So you think of this as derived database. And this is again for decision-making purposes. So we'll be doing some transformation in the original data set. And the intent is for that to be used for analytical purposes. So it's easy when we have to query something and inform our stakeholders. So that's OLTP and OLAP. Now let's proceed to the schemas that we can use for analytics. So first is there's star schema, also called as the dimensional modeling. And this is one example that you're seeing here. This represents star schema. So you would have here your main table, also called as a fact table. And I will be reading this for clarity. So the name star schema comes from the fact that when the table relationships are visualized, the fact table is in the middle, like what we're seeing right now, surrounded by its dimension tables, the other tables that we're seeing. The connections to these tables are like the rays of a star. And you'll see that in the next slide. It will be visually obvious. So this is what it looks like. So you have your main table and all of the other dimensions here are linked to that based on the key provided here. So in this case, we have the fact sales table and the dimension product table is linked to that based on the product key. And then there's also the dimension store table, and it's connected via the store key. And same goes for the other dimension tables that we're seeing here, like dimension date table, and the dimension customer table, and the dimension promotion table. Now, the other schema would be Snowflake schema. So what's the difference? So earlier I said there's going to be a better visualization of star schema, and it would be like this. That's why it is called the star schema. So you have the fact table and then the dimension tables. But the difference with Snowflake schema is this. So in Snowflake schema, dimensions are broken down into subdimensions. Snowflake schemas are more normalized than star schemas. Take note of the normalization. But star schemas are often preferred because they are simpler for analysts to work with. So the what you get in Snowflake schema would be the less redundancy because it is more normalized than star schema. In star schema, it is simple to work with, but you have lots of repetitions and redundancies. It's really for ease of access and querying. So here's some comparison again with star and Snowflake schema. So in star schema, the fact tables and dimensions are contained. In Snowflake schema, the fact tables, dimension tables, as well as the subdimension tables are contained. So it could branch out even further. In star schema, it's a top-down model, while Snowflake schema is a bottom-up, because you have all of these um, very atomic subdimension tables, and you will be building the connections. Okay, next. So star schema uses more space because of the redundancy. Again, it's easier to work with. In Snowflake schema, it uses less space. In star schema, it takes less time for the execution of queries because it's already there. While in Snowflake schema, it will take more time because you will have to perform the aggregation again with the different subdimension tables that we have. In star schema, normalization is not used, so it's denormalized. In Snowflake schema, it has some normalization. The normalization depends on how much normalized you want it to be. So our schema, the design is very simple. The Snowflake schema design can be complex because of all of the connections that you have. Star schema, the query complexity of star schema it is low, while the query complexity of Snowflake schema is higher than star schema. It is very simple to understand star schema, and while in Snowflake it is more difficult. And as obvious, there's less number of foreign keys in star schema, and there'll be more in Snowflake schema. And finally, of course, there's going to be high data redundancy in star schema and low data redundancy in Snowflake schema. So generally speaking, it's very easy to work with star schema. But some of the potential use cases of using Snowflake schema would be for use cases when, of course, you want data to be not redundant. And one thing that I normally think of when if I need to use Snowflake schema would be if there's going to be many to many relationship. Star schema would be good for one-to-one, easy to map the different dimension tables that you have. Snowflake schema, if it's many-to-many and you force it with star schema, then you'll end up with a very redundant data set because there's just so many connections. There's many-to-many. So in those use cases, Snowflake schema would be more appropriate. Okay, next. Now that we're done with the schemas for analytics, we'll proceed to the analytics deployment. Um, but of course, before that, you can perform your modeling, your EDAs, so scripted statistics and whatnot. But that's for another course that I'm also teaching. But once you're done with that, if you want to do some modeling, but again, that's optional, you would want your data and analytics in general to be accessible by the users. So how would you do that? How would you deploy those things? Here are some of the tools that I normally use, and these are very popular tools out there. So Power BI and Tableau are very popular dashboard tools, right? Um, so it really depends on the institution that you work with. A lot of the institutions that I work with use Power BI and Tableau. So if it's Microsoft oriented, then more or less you're going to be using Power BI. In some cases, you will also be using Tableau. They're both very powerful dashboard platforms. And you could do pretty much all kinds of visualizations that you want for the most part. Another tool that I also use is Flask, and it's a Python web framework, but it's bare bones, unlike other tools that you're seeing. So that means you have so much configurability in it. You could do pretty much anything, and this is actually what I've been using for the longest time. If I wanted to build models, build any data science or AI or analytics use case, and I wanted to deploy that, then I'll use Flask. But you would need more software engineering skills to pull this off. Although this is quite easy, I would say, to implement. But again, it's bare bones, so it's really up to you to do pretty much everything. So you might have to learn how to do some HTML, CSS, JS for the front end side of things, and Flask is really the back end. But you have to think of all of these things if you wanted to create a full-blown application. But again, this gives you so much power because um, it's so configurable. It's really up to you. And much more recently, you would have Streamlit. So it is a higher level API, and you could easily create dashboards, visualizations, and whatnot using this. It makes analytics deployment much more easier, I would say. So here's a sample snapshot of Streamlit, and this is like the hello world of that, the um, demo that you'll be seeing once you set up your Streamlit, and it's actually very easy to install and use. And I'll show it right now. I'll just switch my screen to that one. So this is the Streamlit demo now. Okay, so if you go to Streamlit documentation, you'll be seeing this. And installing Streamlit is very easy. It's just pip install Streamlit. And right after that, you just use Streamlit hello, and you will be seeing this. Oh, yeah, it just closed. Hold on. Okay, so I had to turn it on again, but you will be seeing this demo, and there's lots of demos here. You can see the things that you could do with Streamlit. There's just so many, right? This gives you so much power. Now, you could go again to the Streamlit documentation. Okay, you can see very cool visualizations here. You can go back there and you just follow it. There's so many documentation and guide in it, but I'd like to show this one. So the first steps here. So if you follow this section right here, and I won't discuss that because it's already here. So it's really creating the Uber pickups.py. You would have something like this, right? This will be your code and it's reading the data from here, uses the Uber data set. And we're gonna create some visualization using that. We're gonna create a dashboard. So if you run that using this command, the streamlet run Uber pickups.py, you will see this. So it is that easy to deploy analytics um, applications using Streamlit. And it is interactive, as you can see. You can zoom in, zoom out, do whatever, right? So the first visualization shows the number of pickups by hour. You could hover, you could see the details and all that. You could modify the hour here for the next viz, which is the map of all pickups at um, 14, which is 2 p.m. Right? And you could do so much more. This is just a basic example. So that's it for the big data analytics module.